Well, I think we'll start kicking off now. As you look around you, you can see that we've got a pretty good turnout, and it shows a great deal of interest in the subject of dampness in buildings. And we've been going now for 30 years in this business, and the business has changed quite a lot. Some of the talks you're going to see and hear this morning will show what the future is for our business, I hope. Some ideas that you'll be able to go away with, along with your mail bags of goodies from Safeguard. When I came in, it looked like the aftermath of the great train robbery. But first of all, Eric, where's Eric?
Here.
You're there. Oh God, what are you planting yourself in the audience for? It's just sort of confused me. I should have given the talk from the balcony, shouldn't I? I'd like to introduce Eric, my colleague, who's going to give you an overview of dampness in buildings. Eric's been in the business for Safeguard for how long? 5 years. Yeah. 5 years. And before that, he worked for Redlands Lafarge on roof coatings. So he's got a great deal of experience, and I'll hand you over to Eric Rirsch. Thank you.
Thanks. Right, well, it's nice to see everybody here today. In fact, I quite enjoy meeting people I hadn't seen for a while, and then I realised I actually got to stand up and say something, so it kind of changed the atmosphere a bit. Right, so talking about moisture movement in buildings, penetrating damp, condensation, and rising damp. So, start with, we all know about rising damp, I think, the water coming up through the ground, into the building, through the wall. And we've got condensation that can occur on a cold surface, on cold masonry, and penetrating damp maybe through wind-driven rain, penetrating the outside of the wall. So, penetrating damp is sort of in an extreme form there.
Thanks, Boris.
Yeah. So, two mechanisms really to think about. You've got liquid water that can run through cracks and joints and defects in the bricks, driven by wind pressure. And you've also got this kind of a general absorption process going on with diffusion through the brick structure and the porosity. So to start with the first one there, with liquid water running through, this shows a chart from the BRE in 1981, and they plotted the times that it took for water to run through. So that was 90 minutes to go through that gap, 90 minutes, 50 minutes up there. And it might have been, I don't know, 5 or 6 hours through the main structure there. So there were differences in the flow times, the time for that water to penetrate through the brick wall there. And the leakage points were largely through bricks and through cracks in the bricks and through defects and through joints. This was a sort of like the worst case situation they had with poor bricks, high wind speed. They found that roughly 50% of the applied water penetrated, so that's a lot, basically came through. And from a physics point of view, the amount of coming through was proportional to the pressure, the applied pressure, so it kind of made sense, the data. This is an experiment that we did at Safeguard, which was actually done to look at flood resistance. So we stuck a big plastic tube onto a flattened wall here. It was a new flattened wall. And then we filled it up to 0.6 metres height. And this is the limit for structural damage of buildings at flood. So this is quite a high pressure, much higher than the situation you would get with wind-driven rain, which would only be actually 0.05 metres, so it's quite an extreme test, this one. What happened was we filled this up and we kind of went round the back and we thought nothing's going to happen for a while yet, but straight away, after a few seconds, water started coming through the joints, and actually these joints look quite good, and through defects as well that you kind of thought at first sight, you thought wasn't really that significant. And this shows a little clip of the rain coming through there. These are the results that we found, and at high pressures, we used the storm dry cream and repointing. We looked at combinations of the two together, and we found that you really need to do the repointing was quite important. At lower pressures, it wasn't so significant, and the storm dry alone was having a significant effect against the control. But the complete repointed system with storm dry gave us a much better waterproof result. And that's a kind of a picture of before treatment and after treatments taken at 50 minutes with the water in the tube to show the difference. The other thing involved with that, we had to look at the repointing, so we developed an additive to improve the adhesion of the repointing additive to the brick to make it more water resistant. On to the second part, so this is water absorption through the brick. This is some data from the Fraunhofer Institute in Germany. This is looking at the profile, so this is the outside of the wall here, interior of the wall, west facing. Brick is wetter on the outside surface, so it's fairly obviously wettest on the outside of the wall. And what they did from taking data like this, they developed a computer model called WFI, and it simulates this kind of thing that they observed in practice through a computer model, and it takes into account orientation of the wall, the house, etc. This shows you, if it will link, that's the kind of thing that's running on a WFI model, and this is what this does is this is the internal temperature here set at 20 degrees, the inside of the room, and this is the outside temperature, how that's varying, and this is the composition of the wall. So you've got different bricks and insulation in there, and this shows you the moisture profile, whether it's raining, and what it does on the inside surface. So you can predict the behaviour through computer modelling like that, which is quite useful. So you can see how, if you change the wall composition, how it affects things. So here's some real data. What they did, they just looked at the relationship between the water that was in the wall, which is the top charts, and the amount of rainfall, driving rain, and you can see that they more or less peak at the same sort of position up the top here and there with a small delay. So again, that makes sense that, you know, more rain, it takes a while to soak through to the wall. So it follows the rain pattern, and they added silicone into a render here, and you can see that as the amount of silicone in the render is increased, the water in the walls decreased. There's also another result here that they, this is about the last one on the Fraunhofer. I know I'm going on about this a bit, but it's quite interesting. There's a wall here without a render, which is the middle one here. Yeah, this one here. And this is with plaster, and actually that is wetter than the one without the plaster. Whereas the one with, again, a water repellent in the plaster is drier. Okay, this is a little bit of work by the BRE comparing different water repellents. They exposed some little brick walls at East Kilbride, and they measured the moisture content after a year, and you can see that the siloxane and silane water repellents gave the best results there. And that's the same kind of approach that we use with storm dry, and here's some data from storm dry applied to a different range of silicate bricks and mortar and stone there, sandstone as well, and you can see that shows a kind of a before and after application, what it's done so it's improving the water resistance in each case, other than the limestone case there, which is a carbonate. And I won't go into that in detail, but there's a reason why, the chemical reason why the silane silicone approach is less successful on the limestone and more successful on the silicate. The upshot of those reactions is that there's a group, a water repellent group, chemically bonded onto the surface, which gives you improved durability in the long run. And here's a slide from a third party where they've looked at water repellency over a 50-year period. Originally applied in 1953, and 2008 went back and checked the water repellency was still there. With Storm Dryer product, we're in the process of applying for BBA 25-year approval on that product. Just a little bit about heat flow. So you've got a wall, starts raining on the wall, what happens? So one thing to think about is the thermal mass. The cold rain reduces the temperature of the wall. You can also get the rain as absorbed onto the surface and it evaporates away and then cools the surface of the wall. And the other thing that can happen is the rain's absorbed by the wall and it changes the thermal conductivity. So that means that the heat flow out of the wall can then increase. So a few calculations, you can see it works out that 2 and 3 are the most important, and 3 in particular. And here's a chart from University of Portsmouth showing how the thermal conductivity changes of the brick. So there's the dry brick here at 0.6. And when the brick becomes wet, it's up to the thermal conductivity is 1.5. So there's kind of twice as much heat flowing out of that wall in that situation. So this is the first part of penetrating damp conclusions. So there's 2 processes to consider: the crack penetration and the general absorption through the porous structure. Worst case, you could say maybe roughly half the applied water actually penetrates. That seems very extreme, but we'll say worst case. Preferred remedial measures are the combination of crack sealing and surface hydrophobing. Okay, second part on condensation, which we've all seen. General problem is, this is from a BRE guide, is that the moisture is generated in the house, it diffuses through the house, condenses on the cold surface. A few basic things about, because relative humidity is quite a confusing subject. It's easy to get kind of lost in it. So air at certain temperature can contain a certain amount of water vapour. But what happens is warm air can contain more moisture vapours. So when that warm air becomes cold, then the air, the extra water that's in there then diffuses around, finds a cold surface and condenses on that surface. So another way to kind of look at that is in terms of numbers. So if we had a cubic metre of air, say there might be 10 grams of water vapour in that cubic metre of air, which is this case here. So at 25 degrees C, we've got 10 grams. And the amount of water vapour that air can contain is 23 grams. So the humidity, the relative humidity, is just the ratio of those 3, which is 42%. As the air gets colder, you've still got 10 grams of water, but the amount of water that the air can contain is down to 12.8 now at 15 degrees C. So the humidity now goes up to 78% RH. And you get to 5 degrees C, that air can only now contain 6.8 grams of water. So that means there's 3.2 grams around that's going to condense on something, whilst the remainder is at 100% RH. So that's the process that goes on with condensation. It's interesting to calculate, well, if you're sort of that way inclined, it's interesting to calculate the volume of water in the air in a room. So if you said we had 80% RH and 25 degrees C, the amount of water that works out is 19 grams per cubic metre of air. And you can look this kind of thing up through a psychometric chart. So the volume of the room is 40 cubic metres. So the amount of water in the room, in the atmosphere, is 0.76 kilos or 0.76 litres. So in a house, maybe there might be 5 litres then, just to get that as a number. We'll refer back to that shortly. Looking at the sources of moisture in a house, and this is taken from a book drafted by Peter Trotman at BRE. So typically in a new house, there might be 5,000 litres of water present when it's built. So there's a lot of water in a new house due to the building materials. And then you add the people, and these are the different activities, the moisture generated by each of the different activities there. And you can see that some of these are quite high, cooking, drying clothes in particular there. So if you add all that up, maybe 2 people, you might generate 9 to 12 litres per day. And just comparing that, well, I was saying that there was maybe 5 litres in the house naturally there in the air. Some general points about condensation. In the winter, the humidity is great on the inside of the house, so there's a general movement of the water trying to go out of the house. And what tends to happen is that it can condense on a cold wall, either at 2 points, either on the inside surface of the wall or sometimes in the interior of the wall, which we'll hear a bit more about later. And the amount of water that's visible also depends on the ability of the surface to absorb it. So if you had a solvent-based paint which was very water-resistant on the wall, it would be quite striking where the water was. But if you had a kind of a porous structure, maybe like gypsum, unpainted, it will disappear inside and you won't be aware that it's there. The last point on that is that the temperature of that internal surface of the wall has quite a big difference on the condensation. So by using a little bit of insulation, you can improve the condensation side of things. And this is taken from some build desk software where you can calculate the tendency for condensation to occur. The line's gone. All right. The top line is the inside air temperature, 20 degrees C, and this is how the monthly temperature is changing through the year. This is the case for Edinburgh with a solid wall and gypsum. And these 2 lines that I've circled there, one is the inside air temperature, which is this one, and the one above it is the temperature for condensation to occur. So you can see through this kind of analysis that there's going to be condensation running from October through to March, and then get out of the winter period, then things improve. And by changing the structure of the wall, which we've done there, just model different situations, you can see you can remove the condensation tendency like that. Conclusions. Significant amount of water just present naturally in the air. People generate more, 9 to 12 litres per day. House drying can be significant if it's a new house. There's a flow in winter from inside to outside, and it can be benefits from insulation and vapour control in reducing condensation. So you might have a situation, oh sorry, it's not very visible that. You kind of got 5 litres in the air. Construction will add a high amount to begin with, which decreases, and the people come along and start adding more. Okay, rising damp. Again, a sort of extreme slide of rising damp. Looking at building materials, bricks and mortar, and when they're produced and made in the first place, they're made quite often with water. And what happens is, say, when you're firing a brick, the water evaporates away. You end up with pores in the structure, which then cause some transport, allow some transport of water to subsequently occur. And the water will then travel up through the pore structure. And it's this capillary force that drives the upward movement of water. And this force exists because the water just likes the side of the capillaries that are around it. It likes to be attracted to those surfaces when that's the driving force of this mechanism. And through some simple sort of physics equations, you can start calculating if the radius is such a width, then you get capillary rise. You can get to 1.4 metres with a 0.1 millimetre pore size. But the limiting step can actually be just how the speed of transport through that capillary. Here's some pictures from Graham Coleman, who's here somewhere, showing rising damp. The other thing to think about is hygroscopic moisture. So what happens is the process of rising damp, the water's coming up through the ground, it evaporates away, and any salt that was in that water then gets deposited in the wall. And the salt that's there can then attract moisture itself. So you have a situation like this, even if you put some damp proofing in, you've still got the salts left there. You might have got rid of the water, but there's still the salt there. And these salts, what are they? Sodium sulfate, sodium chloride, potassium nitrate. They're the kind of the common three. And there's an Agremont test, a Belgian Agremont test, has a mixture based on those three as a standard salt challenge mixture. But the precise mixture depends on where you are. And this is some data we took at Safeguard. We analysed some different mortar samples from around the UK, and you can see that sulfate figured pretty highly there, and chloride as well as calcium. But it was very varied depending on where you were in a particular situation. So, and this is what they look like. The salts, you can see, this is a gypsum plaster sample where the salts crystallise on the surface, and up the top of the sample, the gypsum plaster started to sort of bubble. And what's going on inside that is that the salt is crystallising inside the pore structure and destroying the integrity of the gypsum, which is then breaking that slowly apart. And that's this strong crystallisation force that's driving that. Pictures of salts occurring. And again, the subject comes up probably every couple of years. There's a conference about salt damage to historic buildings because it's quite important to maintain as quite a big failure mechanism for historic buildings. Right, the kind of overall thing on rising damp is that it's a balance between different processes occurring at the same time. You've got, on the left-hand side there, you've got capillary moisture and hygroscopic moisture. So that's the salt moisture and the capillary moisture. That's increasing the amount of water that's in the wall. And on the right-hand side, you've got evaporation, which is reducing it. And the equation down the bottom was developed by a guy called Mason in the 1970s, and then more recently by Hall and Hoff. But that pretty well governs that whole balance that's going on there. So just looking at some of those terms, you've got wall thickness is a factor, and you can see that because in the right-hand case, there's proportionally less evaporation compared to the left side. That means that with a thicker wall, you're getting higher rising damp. Here's a sort of classic picture that was taken of a 3.1 metre height of rising damp, but the wall's something like 4 metres thick here, so it's, a massive wall. Second thing is the sorptivity there, which controls things, and this is the kind of the suction factor of water being drawn up into the structure. So it's porosity that's influencing that. And here's some of the numbers that we took from those on sorptivity from some of the samples we collected, and very varied those numbers were. We got to 14 on one case and 0.3 another, so it's very variable. But this is a controlling factor in what's going on with rising damp. And evaporation, of course, is another factor. So if you actually put maybe some impermeable wall covering on there, the tendency can be to just drive the rising damp front more higher. Conclusions. So the origins capillary rise, drawing water into the structure, you can get over 1.5 metres. It leaves water in the capillary pores, and then you get this second contribution from salts that then attract water. And importantly, there's this equilibrium process with evaporation from the structure. Magnitude of the effect, so just lining all these three things up together. So for a high sorptivity mortar, which is like one of the high ones there, you might get, you can calculate out 0.7 litres per day per metre length of wall, would be the worst case rising damp situation. So 40 metres of wall around the house, you go through the numbers, you might end up with 14 litres per day. So comparing that, going back to those numbers, we had sort of 0 to 16 on penetrating rain, 9 to 12 for condensation, and now we've got 0 to 14. So I guess it's sort of similar orders of effects, really. But, you know, with a good house, it's quite easy to get kind of zeros on the top and the last contributions there, but the condensation is probably the harder one to control there, really. But actually, yeah, as I say, wouldn't really just a few measurements on test walls, actually. Here's a little time-lapse video of rising damp occurring. Yeah, sorry, right at the beginning, this kind of different light colour at the beginning is to do with the plaster being a bit lighter, but you can see rising damp coming up through the structure there. And you start seeing little bits of salts crystallising out here and there. Annoyingly, when this gets right to the end, you've got the perfect example of salts, and then it goes back round again. So watch out for the end, because the salts start appearing a little bit more in the last phase there. Okay, there. Okay. Oops. Oh, right. So we built some flattened walls from different mortars to look at the how much water there was actually in the wall. We left these walls for 6 months and then took them apart, and then we weighed the bricks and the bits of mortar to see kind of where the water was. So this was the result from a modern, we'll call it a modern mortar, 5-to-1 sand to cement with a plasticizer. And you can see, I don't know, after 6 months, there's not really much rising damp there. It's only gone up 1 or 2 courses of bricks. And then we built some walls with a kind of a porous mortar, replicate the old-fashioned type. And this was the result we got from that. And you can see that there was much higher moisture contents in the wall there. So the same bricks were used, flattened bricks were used, so the dominating thing there is you can see the mortars controlling what's going on significantly. Just a couple of slides on DPC. So the 2 steps to curing RIB with a chemical DPC is the injection of the DPC and replastering. And the 2 types of the chemical type work by either making the pores hydrophobic, which stops this capillary rise effect on the left-hand side, or blocking the pores on the other side. And that's kind of injection mortars work like that on the right-hand side. So they work by 2 different mechanisms. With the Safeguard product dry zone, it works by the left-hand side, the hydrophobic pore method. And that's based on a siloxane. Replastering is important as well, because you've got to worry about the salts. They tend to be higher up, a little bit further up the wall, and the reason for that is there's most evaporations occurring around that area. And this shows what happens with, on the right-hand side in a test, that's a gypsum plaster. You can see the salts, it's been replastered with gypsum. You can see the salts quite progressed a long way up there, whereas on the left-hand side, we got a cement render with a salt block, and you see there's a difference in the lab test performance. So generally, cement-based plasters or renders are used for replastering work. So many alternatives available. Physical membrane is the complete answer, really. But good chemical methods are good practical alternatives. Working by either hydrophobic or pore blocking mechanisms, replastering is important. So those first 3 bits are about, okay, getting moisture in the building. So, you know, what in a way, what does it do? Here's a report, World Health Organization report talking about damp and mould, and they point out that sort of, humid walls create coldness and makes more heating necessary. So, and there's a large proportion of buildings that are damp for one reason, or one of these three mechanisms. So a little bit about absorption of water. So building materials absorb water from the air to different extents. And they also absorb liquid water from the air to different extents as well. And once the water's in there, it can lead to decay by mould and rot. This is a chart from Protometer, and it shows you that, say if you took a situation at 80% RH with a brick, it might only, if you put a brick in an atmosphere of 80% RH, it might absorb up 3% moisture, go up to 3% moisture content, where with wood might be something like 18%. So there's a different tendency from different materials to absorb moisture. Here's some examples of rots that are in buildings. So some pretty horrible ones. This looks like under the kitchen cupboards, that one. And that's a good one, isn't it? So factors in controlling mould growth: temperature, humidity, and the substrate. Does it contain nutrients? Are there salts there as well? And what the porosity? So substrate itself again. pH is another variable. With highly sort of alkaline and highly acidic surfaces, there's no tendency for growth. But so concrete to start off with might be pH 12 or 13 when it's new, and it's actually quite resistant to mould growth or algae growth. But with time, the carbonation occurs, and it makes the surface more neutral, and then mould and algae can start kicking in on a concrete surface. Here's some data lab data looking. This is from a guy called Magan at Cranfield, and they're plotting here the growth rate of different moulds. So in the situation, so the numbers here, 2.5, that's how the rate of growth. So the rate of growth is highest at the 2.5 number at the top, and pretty slow at 0.01 there. And so kind of on the right-hand side, it's a bit too hot, too dry down the bottom, too cold on the left. But the ideal temperature is probably 28 degrees C and 95% RH, so warm and damp really in simple terms. And this is data from Lund University showing the difference this is growth rates occurring on different materials. So plywood is on the bottom there, and it's showing that after 3 weeks at 95% RH, there's a significant amount of growth on plywoods, whereas on asphalt paper, there's very little. So differences on the substrates. And again, Lund looked at, sort of ranked all the different materials in terms of their sort of critical mould growth, humidities and temperatures. So one end of the range, you've got pine, sapwood, which, so 75% RH, there's growth occurring. Whereas down the other end, you've got to go to expanded polystyrene, it's 95% RH. So it's very material dependent whether mould's going to grow on that or not. Okay. Into the home straight now. So I've done some work. We've worked with Andy on a couple of projects. We retrofitted a house in Hereford for insulation purposes, exterior and interior, internal wall insulation. We put data loggers in the wall to measure the moisture. Well, to answer the question, is there moisture build-up really that's going to occur? This is just showing some pictures of the work that was done. Exterior insulation on. I mean, the owners wanted to keep the brickwork on the front visible for the appearance, from the appearance point of view. We putting the data loggers in the wall, and this is the kind of data that we're generating on this project. It's measuring the temperature. You can see daily cycles going on there, and we can measure the temperature sort of from the outside of the wall and on the inside of the wall. What's happening is It's interesting just to see that on the outside of the wall, it's probably about hottest at 4 o'clock in the afternoon on a summer's day, and then there's a kind of a wave of heat that then travels through to the inside, and it might be, I don't know, 10 or 11 o'clock at night, because that's the hottest part then. So there's a kind of a heat wave that kind of goes through the house. But actually the main reason for doing this was to look at moisture, but you start seeing some other interesting effects. And we treated part of the house with storm dry, and we've seen this is after 12 months, actually a little bit further along now, but that the moisture sensors are saying that part's drier inside the wall now on the treated side compared to the untreated. So the sort of questions this is trying to answer: does water repellent help reduce mould risk with internal wall insulation? How do humidity levels for mould growth in the lab correspond to the in-wall data? So that, you know, what happens here, and how does that compare with what Lund University found? So there's another interesting thing. And what are the risks with internal wall insulation, which is a concern to Andy. Right, thank you very much for your attention.